So, imagine this scenario. It's Friday night. You get a notification that tickets for like the IMAX 70 millimeter re-release of Interstellar or Oppenheimer just dropped on BookMyShow.
Yeah.
And you are racing against the clock. Your pulse is actually quickening. You open the app. You find the perfect middle seats, row F, right in the center. Right, the golden seats. And you click select.
That specific moment is pure adrenaline. I mean, it is the modern digital gladiator arena.
It really is. But here's the thing. You hesitate for a split second.
Yeah.
Maybe you're checking if your friend actually replied to the text to confirm, or you're scrambling to find your credit card in your other jeans.
Classic mistake.
Exactly. And in that split second, your heart is pounding because, literally thousands of other people are looking at that exact same screen layout.
And they are all gunning for row F.
Right. And this brings up the nightmare scenario. Like, what happens if someone else clicks those seats at the exact same millisecond? Or let's say you do click them, you get the lock, but then you get distracted. You come back 10 minutes later to pay. Do you still own those seats?
Or have they been snatched away?
Exactly.
That right there is the million-dollar question for theater owners and, well, the absolute frustration point for users. It's the difference between a sold-out show and an empty seat.
So today on the deep dive, we're peeling back the interface. We aren't looking at the pretty movie posters or the seat colors.
No, we're getting into the weeds.
We are doing a deep dive into the low-level design, the LLD of a booking system like BookMyShow.
Right.
And we're basing this on a technical breakdown by Shobh Patel, which is excellent because he doesn't just talk theory.
He really gets into it.
Yeah, he walks through the actual code logic, the class diagrams, and specifically the failure scenarios.
It's a great resource. It really bridges the gap between, I want to build an app and how do I actually handle 10,000 people clicking a button at once?
Right. So the mission for this deep dive is to understand the invisible traffic cops inside the code.
The traffic cops. I like that.
We're going to tackle three main monsters today: the seat clash, the ghost booking, and the massive crisis that happens when you try to scale this from one server to many.
The scaling crisis is where things really get interesting. That's where the junior engineers get separated from the senior architects.
Oh, absolutely.
But you're right, we have to start with the foundation.
Right. Before we get to the locking wars, we have to look at the blueprint, because the source material starts with the requirements. And there was one word that kept popping up.
Extensible.
Extensible, exactly.
Yeah, this is a classic software design challenge. Beginner's code for today, but architect's code for tomorrow.
Right.
In the breakdown, the example given is seat types. Right now, a theater might have regular seats and recliner seats. Regular is 150 rupees, recliner is 300. Simple enough.
But theaters are getting fancy. Next year, they might want VIP seats.
Or those 40X seats that shake.
Or bean bags.
Exactly. No, if you wrote rigid Kodiak, you'd have if statements scattered everywhere.
Like, if seat is regular, do this.
Right. Also, if seat is recliner, do that. And every time the business wants to add a beanbag, you have to go into the core code, find every single if statement, and modify it.
Which sounds like a nightmare.
It is a recipe for bugs.
Yep.
You break one thing, the whole system crashes.
So how does the design and the source material actually solve this?
They use an abstract class for the seat. Think of it as a template or a contract.
Okay.
The parent class seat holds the common stuff, the seat ID, the row, the base logic. Then specific classes like regular seat or recliner seat extend that parent.
So if I want to add a VIP seat later...
You just create a new class, VIP seat, extends seat. You define its specific price logic inside that new class.
Got it.
You don't touch the existing regular seat code at all.
Oh, that's the open-close principle from Solid, right?
Bang on. Open for extension, close for modification. It allows the system to grow without risking what's already working.
That makes a lot of sense.
And they applied this exact same logic to payments, which I thought was really smart.
I noticed that. The strategy design pattern.
Yes. This is one of my favorite patterns for e-commerce. Think about how many ways you can pay today.
Card, UPI,
Net banking.
right? And tomorrow it might be crypto.
Or some generic wallet.
Yeah.
Or buy now, pay later.
Exact.
Instead of a massive block of code checking how you want to pay, the system treats payment as a strategy.
Okay.
The pay function doesn't care about the details. It just says execute payment.
So it creates a plug-and-play system.
Precisely. If the user selects UPI, the code plugs in the UPI payment strategy. If they select card, it plugs in card payment strategy.
And the thing that decides which plug to use, that's the factory design pattern.
The factory. The source described it almost like a traffic controller.
Right.
I actually like to think of it like a vending machine. You press C4 for a Kit Kat. You don't need to know how the coils turn or how the machine grabs the bar.
You just want the Kit Kat.
Exactly. The factory is that machine. You give it an input. User wants UPI, and it hands you back the correct strategy object to handle the logic. It keeps the messy decision-making code in one place, so the rest of your app stays clean.
Okay, so we've got our clean code, we have our factories, our strategies. Now let's talk about how the data is actually stored.
The data structures.
Right. The source noted something interesting about how theaters and screens are linked.
Oh, the map versus list thing.
Yes. The theater class holds the screens in a map, not a list. Why does that distinction matter?
That is a very deliberate performance choice. Imagine you are the code. You have a list of 20 screens.
Okay.
If I ask you for screen 15 and you have a list, you might have to check screen 1, then screen 2, then screen 3.
All the way to 15.
Right, all the way to 15. That's linear time, or big O of n.
Which is fine for 20 screens.
No.
But what if we're talking about thousands of data points?
Exactly. With a map, specifically a hash map, you don't search. You just look up the key.
You just jump right to it.
Yes. You say, give me screen 15,
Yeah.
and the map gives it to you instantly. Constant time, or big O of 1. When you are building a system like BookMyShow that needs to handle millions of requests, those microseconds saved by using a map instead of a list add up to massive performance gains
It's the difference between flipping through every page of a book to find a word.
versus just looking at the index.
Perfect analogy. And when you have a million users, you definitely want the index.
You need the index.
Okay, so the stage is set. We have our classes. We have our data structures. Now let's get to the drama. The seat clash.
The concurrency problem.
Yeah.
This is where friendships are tested.
Truly. The source describes a specific scenario to illustrate this. We have user 2 and user 3. User 2 wants seats 3 and 4.
Okay.
And user 3 wants seats 4 and 5.
Right. So seat 4 is the battleground.
Exactly. It's the overlapping desire. They both hit proceed at the exact same moment. What happens inside the system?
This is where we introduce the log provider. You see, you can't just write to a database immediately.
Why not?
That's too slow. And databases are hard to synchronize at that speed.
Yeah.
You need a way to say, I am holding this in memory. So the system generates a unique key.
What does that T look like?
It's usually a string combination.
Fair.
Something like showid_seatide. So Jurassic Park, 12 p.m., seat 4.
Got it. That string is the unique identifier for that specific asset.
Exactly.
And where does that key go?
In the initial design, the in-memory version, it goes into a concurrent hash map.
Wait, hold on. You emphasized concurrent there.
I did.
Why not just a normal hash map like we talked about for the screens?
This is a crucial distinction. A normal hash map is not thread safe.
Meaning what?
If two threads, user 2 and user 3, try to write to a normal map at the exact same nanosecond, the internal structure of the map can get corrupted.
Oh, wow.
Yeah, the program could crash, or worse, it could enter an infinite loop.
So a concurrent hash map is built to handle the chaos.
Exactly. It has internal locking mechanisms. It allows multiple threads to read and write without stepping on each other's toes.
Okay.
I mean, an action either happens completely or not at all.
So walk us through the race. User 2 and user 3 race to the try-lock function.
Correct. They both call try-lock. Now, even though it feels simultaneous to us humans, the computer works sequentially at the micro level.
One of them will get there first.
Exactly. Let's say user 2's thread arrives a microsecond faster. The system writes the key for seat 4 into the map.
And user 3.
When user 3's thread arrives a microsecond later, it checks the map. It sees the key. Jurassic Park, 12 p.m. seat 4 already exists.
Oh.
So the try-lock function returns false.
Denied.
Denied. And here's where the user experience design comes in.
How so?
User 2 wanted seats 3 and 4. User 3 wanted 4 and 5. User 3 could have had seat 5. Nobody else wanted seat 5.
Right.
But because they failed to get seat 4, what happens?
The entire booking failed.
Yes. It's an all-or-nothing transaction.
That seems harsh. Why not just give them seat 5?
Because that's a terrible user experience.
Yeah.
If I'm going to the movies with my partner and the app says success, you got one seat but not the one next to it?
I'm going to be furious.
Exactly. You don't want to sit alone.
Yeah.
So the system throws a seat not available exception for the whole request.
So user 3 gets the error message and user 2 goes to the payment page. Victory.
Victory, for now. But having the lock is only half the battle.
Right, because now we enter the next circle of hell, the ghost booking.
Or technically, lock expiry in TTL, time to live.
This is a business problem as much as a technical one.
Absolutely.
The source explains that theater owners want to maximize profit. If I lock a seat, I am preventing anyone else from buying it.
You're taking it off the market.
Right. And if I decide to go make a sandwich, or I realize I'm broke and close the browser, that seat is dead inventory.
Exactly. You are holding the inventory hostage. No one else can buy it, but you aren't paying for it.
So what's the fix?
The system enforces a TTL. In the real BookMyShow app, the source mentions it's usually around 8 minutes.
Okay.
For the code demo in our source, they set it to 5 seconds, just to show it happening quickly.
So how does the code actually know time is up? Is there a little stopwatch attached to every seat key?
In a way, yes. Remember that map where we stored the lock?
The concurrent hash map?
Right. We don't just store locked. The value associated with that key is an object, an expiry object.
What's inside the object?
2 critical things. The owner ID, which is who locked it, and the deadline.
And the deadline is just the current time plus the TTL.
Correct. So if I book at 12:00 and the TTL is 8 minutes, the deadline is strictly 12.08.
Okay, but you need a way to clean these up. You can't just wait for someone to check the seat.
You need an active janitor?
The source calls it the sweeper.
I love that name. Technically, it uses a scheduled executor service.
Wishes.
It's a background worker thread. It wakes up on a schedule, say, every 1 minute, and scans the entire map.
Just constantly checking.
Yes. It looks at every key, checks the deadline, and if it's past 12.08, it deletes the key, it frees the prisoner.
This leads to the most dramatic scenario in the source material, and honestly, the one that I think confuses users the most.
User 4 versus user 5.
Yes, the user 4 versus user 5 conflict. I want you to walk us through this slowly because this is where the UX and the back-end logic really collide.
This is a crucial edge case. Let's trace it.
Okay.
User 4 selects seats. They get the lock. The map says user 4 owns this until 12.08. They proceed to the payment page.
So they are looking at the credit card form, they are typing in their name.
Yes, but user 4 is slow. Maybe they are finding their wallet. Maybe they're waiting for an OTP.
Right.
The clock hits 12.08.01. The sweeper wakes up, sees the deadline has passed, and deletes the lock.
Boom.
The seats are now free in the system.
But user 4 is still staring at the payment page. The page didn't refresh. They don't know they lost the seats.
Exactly. Their local browser still thinks they are in the process. Now, user 5 comes along.
Okay.
They see the seats are available because the lock is gone. They select them. They get the lock.
Yep.
User 5 is now the owner of those seats in the system's eyes.
Meanwhile, user 4 finally finds their wallet. They type in the number and click pay.
And this is the moment of truth. The confirm booking function is called.
Does it just take their money?
No. Before it takes the money, it performs one final critical validation check. It calls is locked by for user 4.
It's like the bouncer at the club checking your hand stamp one last time before letting you into the VIP section.
Great analogy.
Mm-hmm.
And what does the system see? It looks at the lock. It sees a lock exists, but the owner is now user 5. So it returns false.
Ouch. User 4 gets an error message. Lock ownership mismatch or seats unavailable.
It's brutal.
That is painful. You think you have them, you click pay, and you get rejected.
It is painful. But consider the alternative.
That's that.
If the system didn't check ownership at the very last second, user 4 would pay for seats that user 5 already holds.
You'd have a double booking.
That would be a customer service nightmare.
So the system prioritizes fresh locks over stale payment attempts.
Always. It prioritizes the current valid state of the data over the user's session state. It has to.
Okay, so we've solved seat clashes with locking, and we've solved lazy pairs with the sweeper.
We have.
But there is a huge elephant in the room that the source brings up in the final section.
Ah, yes. The scaling crisis.
Because everything we just discussed, the concurrent hash map, the sweeper, it all lives in the memory of the computer running the code.
Right, which is fine if you are running a small Cinema website on one single server, let's say one EC2 instance on AWS.
Okay.
The map is in that server's RAM. User A and user B both connect to that server, so they are looking at the same map. They're playing by the same rules.
But then the Avengers movie comes out.
Traffic spikes.
Your one server is crashing. So you do what any good engineer does.
Yeah.
You add more servers. Now you have server 1 and server 2 and a load balancer distributing the traffic.
And this is where the in-memory design completely falls apart.
Why?
Imagine user 1 connects to the load balancer and routes them to server 1. User 1 locks seat A. That information is written into server 1's RAM.
Okay. So server 1 knows seat A is taken.
And server 2 doesn't. They don't share RAM. Oh. Now user 2 connects. The load balancer, trying to spread the work, routes them to server 2. User 2 wants seat A.
Right.
Server 2 checks its own RAM. Does it see a lock for seat A?
No, because server 1 has the lock, server 2 knows nothing about it.
Exactly. It's a split brain problem. Server 2 sees the seat as free. It grants the lock to user 2.
And now you have two people with valid bookings for the same seat on the same night.
Which means a fistfight in the cinema aisle.
So how do we fix this? The source is very clear that in-memory is not production ready for this exact reason.
We have to move the state locks out of the individual servers and into a shared external storage.
Okay.
The source recommends a distributed lock provider, specifically Redis.
We hear this name a lot in tech, Redis.
It's everywhere.
But why Redis? Why not just a regular SQL database? We already have a database for the movies and theaters.
Speed, pure and simple. A traditional SQL database writes to a hard drive or an SSD.
Right.
It's designed for durability in complex queries, but reading and writing to disk is slow compared to memory.
Makes sense.
Redis is an in-memory data structure store. It lives in RAM, just like our hash map did, but it runs as a separate service that all the other servers can talk to.
So it gives us the speed of RAM, but the shared access of a database.
Exactly. It's fast enough to handle the millisecond race we talked about at the start.
So how does the architecture change with Redis in the middle?
Now, Redis acts as the town square. When user 1 hits server 1 and tries to lock seat A, server 1 doesn't write to its own RAM.
It reaches out to Redis.
Yes, it writes the lock there.
And when user 2 hits server 2,
Server 2 also reaches out to the exact same Redis instance. It asks, is seat A locked?
and Redis says, yes, server 1 just wrote a lock here.
So server 2 denies the booking.
So Redis becomes the single source of truth.
Exactly. It decouples the application logic from the data state. You can have 50 servers or 500 servers.
Right.
As long as they all check with Redis before allowing a booking, you will never have a seat clash.
That is such a crucial shift. It's the difference between coding for a homework assignment and coding for a real company.
It really is. And I want to point out one clever thing in the code provided. The lock provider was designed as an interface.
Remind us why that matters.
An interface basically says, I promise to have a lock method and an unlock method. The rest of the app doesn't care how it locks.
Okay.
So when the developers realized they needed to switch from in-memory to Redis, they didn't have to rewrite the whole booking engine.
They just swapped the in-memory strategy for the Redis strategy.
Exactly. They just plugged in a new implementation Redis lock provider, the code that handles payments, the code that handles seats. It didn't even know the difference.
That goes back to the extensibility we talked about at the very beginning.
It all connects. Good design anticipates change, whether that's new seat types or moving from one server to a distributed cluster.
It's a great example of how booking a ticket seems simple on the surface, just a few clicks. But underneath, there's a complex dance of ownership, timing, and synchronization.
It really changes how you look at that processing spinner on your screen. You know that behind the scenes, a thread is desperately trying to write a key to a map before someone else does.
And hoping that your 8-minute timer hasn't run out.
Exactly.
Now, before we wrap up, here is something to think about. The source mentioned that the locking logic is separate from the booking logic.
Right.
We rely entirely on Redis for the locks, but systems fail. What happens if Redis goes down?
That is a terrifying thought for an engineer.
Think about it. If the lock provider fails, does the theater show everything as available because no locks can be found?
If so, you get massive double bookings.
Right. Or does it show everything as sold out just to be safe?
Usually you'd fail closed, meaning you stop all bookings. You'd rather take the site down than sell the same seat twice.
And here's another angle. In a world of bots and scalpers, is an 8-minute TTL actually too generous?
Oh, absolutely.
Because if I have a bot farm, I could have thousands of bots locking every seat in the theater.
They hold them for 7 minutes, 59 seconds.
Right. They release them and immediately lock them again.
That is a denial of inventory attack. You aren't hacking the system, you're just abusing the rules. You could effectively shut down a theater without ever spending a dime.
It makes you wonder if the future of booking isn't just better code, but better human detection to stop the bots from grabbing the locks in the first place.
That is a whole other deep dive for another day.
Something for you to mull over the next time you see that countdown timer ticking away on your screen. Thanks for joining us on this deep dive into the architecture of movie nights.
Happy booking, everyone.
See you in the next deep dive.